Welcome to Learning with Philemon. In this video, we will be looking at the order in which electrons occupy atomic orbitals. In the orbitals video, we saw that electrons can occupy differently shaped atomic orbitals within an energy level. We need to consider three principles. Firstly, according to the Aufbau principle, electrons occupy the orbitals of lowest energy first. In the diagram, we see the orbitals placed in order of increasing energy. In the first energy level, only one s orbital is available, so electrons would occupy this orbital first. In the orbitals video, we discussed that according to Pauli's exclusion principle, two electrons occupying the same orbital must have opposite spin. This is denoted by the arrows pointing in opposite directions. If more electrons are added, these would occupy the second energy level. As the s orbital is lower in energy than the p orbitals, the electrons first occupy the 2s orbital. Note that the number 2 indicates the principal energy level. The next orbitals in energy to be filled are the 2p orbitals. Here, Hund's rule applies. The orbitals are filled first singly before they are doubly filled. This prevents the repulsion of having two electrons in the same orbital. This would be the electron configuration of nitrogen. If three more electrons are added, the 2p orbitals fill up. The 3s and 3p orbitals are filled in the same way. At this point, we reach an interesting deviation. We would expect to fill the 3d orbitals before the 4s orbitals, as the 3d orbitals are in a lower principal energy level. However, the 4s and 3d orbitals are very close in energy. For the elements potassium and calcium, which are in period 4, the 4s orbitals are in fact lower in energy than the 3d orbitals, as depicted in this diagram. In the IB and A level, it is not discussed that this diagram is not accurate for the elements after calcium. For elements such as scandium in the D block, the 3d orbitals are in fact lower in energy than the 4s orbitals. However, this diagram is useful at IB and A level to determine accurate electron configurations, so we will stick to it. If you want to read more into why the 3d orbitals can be lower in energy than the 4s orbitals, check the link in the description. In the case of this element, we fill the 4s orbitals before the 3d orbitals. This diagram can also be called an orbital diagram. Sometimes the orbitals are drawn as a box instead of a line. Don't let this confuse you. A quicker way to describe where electrons are is to write an electron configuration, seen in this slide. This orbital diagram is actually for the element zinc, Zn. The numbers in an electron configuration represent the principal energy level, 1, 2, 3, etc. The letter represents the orbital, s, p, or d. The exponent represents the number of electrons. For example, these electrons are in the principal energy level 3 in d orbitals, and there are 10 of them, hence the term 3d10. The orbitals are written in terms of increasing energy, following the Aufbau principle discussed. Hence we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Zinc has an atomic number of 30, so it has 30 electrons. If you add up all the exponents, you will see this adds up to 30. Because starting from the 1s orbital can take a lot of time, and lazy chemists like myself like shortcuts, you can write a noble gas configuration. You simply find the noble gas in the previous period. The noble gases are the last group of the periodic table. For zinc, this is argon, Ar. Argon has an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6. So up to this point, you need to add the 4s and 3d electrons. So zinc has a noble gas configuration of Ar, 4s2, 3d10. To write electron configurations, some students remember the order of the orbitals and count the total number of electrons. Some use the periodic table. The periodic table is an incredible tool for a chemist, as it provides more information than you would expect. In this dynamic periodic table, see the link in the description, you can see the electron configuration of each element. Now, of course, you do not have this in your periodic table, but this one will help me demonstrate the point. The first two groups of the periodic table are considered the s block, because the last term in the electron configuration will always be an s orbital. For example, for beryllium, this is 2s2. Groups 13 to 18 are considered the p block, because the last term in the electron configuration will be a p orbital. For example, fluorine is 2p5. Groups 3 to 12 are considered the d block, because the d orbitals are occupied. For example, for nickel, we see the term 3d8. In the periodicity topic, you will learn more about these parts of the periodic table. Another interesting trend is that the group number helps us identify the number of electrons in the last orbital. All the elements in group 1 have one electron in the last s orbital. For example, 5s1 for rubidium. All the elements in group 2 have two electrons in the last s orbital, 5s2 for strontium. From groups 13 to 18, the number of electrons in the p orbitals increase by 1 each time, p1, p2, p3, p4, p5, p6. The d block is similar to the p block with a few exceptions that we will discuss. Using the orbital diagram, you would expect the electron configuration of chromium to be 4s2 3d4. However, the electron configuration is in fact 4s1 3d5. It turns out that it is more energetically favorable to singly fill all the orbitals that are very close in energy. This relieves the electron-electron repulsion of having two electrons in the 4s orbital. All elements in this group, group 6, will show this anomaly in electron configuration. Similarly, you would expect the electron configuration of copper to be 4s2 3d9. However, the electron configuration is in fact 4s1 3d10. It turns out that it is more energetically favorable to have the 4s orbital singly filled and all the d orbitals doubly filled. All elements in this group, group 11, will show this anomaly in electron configuration. To consolidate your learning, I would recommend that you practice writing some electron configurations and noble gas configurations and checking them on the dynamic periodic table we have seen or online. Thank you for listening. If you haven't already, please subscribe for more content. Stay curious.